Hello, welcome to the Introductory Physics Lab 2, where we created a movie to observe a motion of a falling object. We compare it we compare the same type of motion but predicted by a computer model governing the equations of drag, gravity, and motion. Now for this purpose I've dropped a tennis ball from a height of 1.8 meters with a weight of 0.056 kilograms. The y direction was chosen to point downward because it's also the location the ball is falling. You can see it fall along the minus y directions with the successive locations being shown as time progresses. The graph shows location as a function of time, all this done in 0 to 0.6 seconds. Now for this to work we have issued the mass of the ball being 0.056 kilograms. The position of the ball is the vectorial component form 0 along the x, 0 along the y, 0 along the z, along with no velocity. Time starts at 0 seconds. Now, in the program, we have to calculate net forces acting on our object because it's accelerating. There should be net forces acting, and the net forces are the weight force and the drag force. Now the weight force is calculated using the calculation weight of the ball times the gravitational acceleration projected in the minus j. The drag force is calculated given a proportionality constant, a cross-sectional area, and the air density with its velocity. You can see that here. The proportionality constant of a ball, which is 0.55 for a tennis ball, for a new tennis ball, times the cross-sectional area of the ball, calculated 2 times pi times its radius squared, which is a value of 0.00342 meters squared. We do times the air density, which is 1.21 kilograms per meters cubed, times its velocity of the ball to the power 2 divided by 2 times j hat in the plus y direction. Now the weight force, which points down, and the drag force that points up, we create the net forces acting, which is an addition of the two forces involved. Now this net force gets plugged into the Newton's second law equation, where we issue a new velocity for our ball using the momentum principle. We calculate a new position for our ball as delta t progresses, just like here. Delta t progression starts here with a progression of 0.001 seconds. You can see that the program runs. If I play it, you can see the ball falling along the minus y. Velocity increases, so the drag force increases. Now these two graphs are combined in the Google Sheets, where we can see the comparison of the observed position in blue, the model position in red. You can see that slope wise it's a very good agreement, but the slope is different here and here. It's slightly different. Now the conclusion of this is that the observational findings, they seem to correlate well with the model predictions, although as time progresses there seems to be a disagreement slope wise of the between the location of the model and the actual observed location. Now this discrepancy you can see in the graph involve uncertainties in air density due to meteorological influences, inaccurate point mass locations due to the increase in blur as the velocity increases in tracker. The angle of recording might also be a factor. The rotation of the y-axis in tracker also plays a role. Now there are also uncertainties in the measurements. They are also a factor because I measured the height at 1.8 meters, but I couldn't be sure, so I set a plus or minus 4 centimeters there. And these effects cannot be underestimated. Thank you very much.